Use this menu to explore the results of our previous work and track your progress through the rest of this module. The horizontal ventilation study emphasized the change in fire dynamics resulting from predominantly synthetic fuel loads, specifically the increased likelihood of the fire department encountering ventilation-limited fire conditions upon arrival. This led to the understanding that additional ventilation without the timely coordination of water application would lead to rapid fire growth. This study also highlighted the need for the fire service to understand flow paths within structures, the impact of closed doors on preserving occupant tenability, and tactical measures to limit the amount of available oxygen entrained into the structure, such as controlling the front door if the fire location is not readily apparent. The experiments conducted as part of the vertical ventilation study reinforced some of the key takeaways from the horizontal ventilation study, such as the increased density of synthetic fuels, the importance of understanding flow paths, controlling the access door, and coordinating activities on the fire ground. One of the new discoveries was the importance of hole placement during vertical ventilation. For a coordinated attack, a vertical ventilation opening placed over the seat of the fire is more effective than an opening located remotely. Additionally, this study brought to light the concept of softening the target with exterior water application during suppression operations. Applying water directly into the fire compartment as quickly as possible, whether from the exterior or the interior, has the most significant impact on occupant tenability and firefighter safety. The positive pressure ventilation experiments reaffirmed the impact of closed doors and exterior water application on occupant tenability and firefighter safety. New findings provided guidance for using positive pressure fans for ventilation, including the size of ventilation openings, inlet to outlet ratio, and the importance of controlling the flow path. The effectiveness of positive pressure attack or ventilation measures is dependent on the exhaust opening size and location. The opening must be of adequate size and should be located in the fire compartment. Additionally, ventilation openings made in compartments remote from the fire may draw and extend the fire into previously uninvolved areas of the structure. Use this menu to review the key findings of the fire attack study. A solid understanding of air entrainment and water distribution is critical to understanding the impact of suppression operations on the fire ground. Click to learn more. Before discussing the impact of air entrainment on suppression operations, we must first understand how a water droplet moving through space entrains air. As water leaves the end of the nozzle, the momentum of the hose stream propels the droplets forward. As the droplets impact the air ahead, an area of high pressure is created. In the wake of the droplets, there is an area of low pressure, which causes air to be entrained and carried forward with the droplet. If we apply these same concepts to hose streams, the impact of air entrainment should be clear. Suppose that you are holding a straight or a solid stream in a fixed position at the start of the hallway. You are flowing water down the hallway without manipulating the stream in any pattern. In this case, you are entraining about 1,000 to 2,000 CFM of air into the hose stream. As soon as you start to manipulate the stream, for example in an O pattern, you increase the air entrained to approximately 4,000 to 6,000 CFM. If we change from a straight stream to a fog stream, the air entrainment increases dramatically. For example, a fixed fog stream entrained approximately 10,000 CFM of air. If we manipulate that fog stream in an O pattern, we can expect to see air entrainment in excess of 15,000 CFM. How we manipulate the hose stream inside a structure can change the amount of air that is entrained. The more broken the droplets, the wider the stream, the faster the pattern, the more air entrained. These CFM values are comparable to those produced by a positive pressure fan, so they can significantly affect fire dynamics and victim survivability during suppression operations. It is essential to understand these concepts when applying these hose streams within a structure. Now, let's look at water mapping, or how water is distributed within a compartment. If we apply a hose stream perpendicular to a surface, the water will radiate 360 degrees. We often picture that as a stream applied straight ahead towards a wall, but let's imagine that stream applied to the ceiling. The steeper the angle into the compartment, the more the water will radiate outwards in all directions, and the better the surface coverage. As the stream impacts the ceiling and the water radiates outward, the momentum of the water carries it across the flat ceiling surface common in residential structures. Once the water has coated the ceiling surface and reaches the side walls of the compartment, it falls down these surfaces in sheets. As the water reaches the floor, it accumulates and pools in different areas depending on the obstructions that may or may not be present. This water application method nearly simultaneously coats all surfaces within a compartment and is effective in fire suppression. Now, let's apply the hose stream into the fire compartment from the hallway or through a window from the exterior. In these cases, you will want to employ a steep stream initially to coat all interior surfaces and rapidly reduce temperatures inside the fire compartment. The drop in temperature causes the fire gases to contract, decreasing pressure, lowering temperatures, and improving survivability in adjoining spaces. Once the interior surfaces have been cooled and we have begun to knock down the fire, we must focus on getting water into the middle of the compartment to limit the likelihood of regrowth. The stream can simply be brought lower into the compartment if operating on the interior, wetting the remaining burning fuels. Then, once the compartment is sufficiently cooled, firefighters can enter the compartment to complete extinguishment. If applying a stream from the exterior, a follow-up water application will be required. For example, suppose the firefighters are located on the same level as the fire. In that case, the nozzle can be inserted into the window and additional water can be applied to the remaining burning fuels. Suppose the firefighters are located on a different level than the fire. In that case, the hose stream can be deflected off the window header to achieve additional distribution, followed by entry into the compartment for final extinguishment. Now let's look at what we have learned about exterior water application. As we now know from studying hose stream mechanics, properly mapping the water inside a fire compartment is the critical factor in the success of extinguishment. This includes water applied from the exterior. An initial application of water into the fire compartment at a steep angle will coat all surfaces inside, providing a rapid change in conditions to benefit any potentially trapped occupants and the overall success of the suppression operation. However, as discussed in the water mapping section, a follow-up application of water is required to achieve additional distribution into the center of the compartment and onto the remaining burning fuels. It is important to understand that utilizing a straight or solid stream during exterior water application is essential to ensure we get the most amount of water into the compartment with the most momentum, the largest droplet sizes, all while entraining the least amount of air. We must also ensure that the window opening is not occluded with the hose stream. An occluded vent will prevent the opening from serving as a low-pressure vent for the exhaust of fire gases. Thus, the fire gases will be redirected to another outlet within the structure. In short, we need the most amount of water in the window with the least amount of air entrainment, and no matter what we do, we should not occlude the opening. We have seen the success of a flow and move approach of interior water application. This approach allows us to take advantage of maximum surface cooling. For example, an O pattern can essentially seal off the space ahead of the advancing hose line. This will prevent products of combustion from coming back over the firefighters while allowing the higher temperature, higher pressure gases behind the firefighters to vent out of the structure. This allows us to take advantage of air entrainment to draw fresh air in behind the advancing crew, improving conditions for potentially trapped occupants and fire crews inside the structure. Once the nozzle team has an idea of the location of the fire, attempts should be made to get water into the compartment as early as possible. This could include deflecting the hose stream off the door frame to the fire compartment. As the nozzle team reaches the threshold of the compartment, the same approach to that of exterior water application should be taken. An initial steep angle will coat all surfaces in the compartment. Once the fire is darkened down, the stream can be brought lower to the remaining burning fuels. After the fire is extinguished, the nozzle team should employ hydraulic ventilation out of any available opening in the fire compartment to aid in the smoke removal from the structure. Understanding the fundamentals of hose stream mechanics is vital to the success of fire suppression operations. This includes knowing when and how to utilize air entrainment to your advantage, understanding when air entrainment can be your enemy, and how to best apply the water through application patterns, stream angles, and deflection methods to successfully map the fire compartments inside a structure. Through these principles, we know that maximizing our surface cooling and utilizing a flow and move approach both on the exterior and interior of a structure can have a beneficial outcome during suppression operations. A simple-to-reference summary of fire suppression conclusions discusses knockback, knockdown, and base fire extinguishment. If the hose stream is being applied from an off-plane position, either into a fire compartment above or below the location of the nozzle firefighter, the hose stream can begin to have an impact by knocking back the fire. Once the nozzle firefighter is on plane with the fire, better mapping can be achieved, and a more effective knockdown can occur. Once the fire is knocked down, the nozzle firefighter can proceed into the fire compartment for base fire extinguishment. The prior research studies have shown little correlation between visible fire and smoke conditions on the exterior and potential occupant survivability on the inside. There are simply too many variables to say with certainty whether a space is survivable for a potentially trapped occupant based merely on the conditions visible from the exterior during a fireground size-up. Consideration should be given to how best to employ search, suppression, and ventilation tactics to have the most beneficial outcome for a potentially trapped occupant. The fire attack study built on previous research on fire service ventilation and suppression tactics. The goal was to provide a comprehensive assessment of the impact of these firefighting tactics on chemical and thermal exposure to firefighters and potential occupants of the structure. Tactical considerations were developed from 3 sets of experiments, looking at air entrainment, water mapping, and bedroom fires in full-scale structures. These considerations provide data-driven insight into interior advancement techniques, the impact of water flow on gas movement within a flow path, interior and exterior water application, and the impact of gas contraction during water flow. For more detailed information and discussion on the tactical considerations developed from the research, download the associated technical reports and check out our online training. This background review is intended to bring you up to speed on the relevant conclusions from previous research before talking specifically about the coordinated fire attack study. If you would like to learn more about any of these topics, please check out the associated reports and training courses.